All right, so my name is Karl. I'm with a company called 2600 Hertz. We're based here in San Francisco, and we build an awesome telephony platform that you guys should check out. But I'm going to talk to you today about some of the ways that we've handled the challenges that have faced us and some of the opportunities that we're giving the people that are using our platform. So the problem is that we have lots of people using the platform. They're all connecting to us throughout various components of the they're connecting the various components throughout the WAN, and we need to address their communication needs in a real-time environment because with the telephony system, people expect it to work every time. They have to be able to pick up a call, hang up. You can't have glitches, and you need to do it very quickly. So the solution I'll be presenting here is AMQP. I'll talk a little bit about what AMQP is, give you an introduction, a little bit about some of the tool sets that it offers, and then I'll go over our implementation. So, like I said before, the problem that we're trying to solve here is when you have lots of components that are either legacy components, you have other parties connecting to you, or maybe you just have an environment where you can't bring in something, like a full Erlang stack. So you already have existing components, or you have different teams working in different components. But all these things have to integrate and work together. You also have to take into account things like growth. You want to be able to distribute this out and handle dynamic loads, peak loads. You might have periods like, for instance, if you're running, so again, in my industry, an SMS app, you might have like voting. And so you have a really high spike, and then you can drop it off. So you only need the resources for a short period of time. So you want to be able to attach things in and pull them off reliably. And then, of course, you have to deal with the wild and woolly WAN, which is, an interesting place. So the takeaway here is that the aces, you put your aces in your places. You use the right tools for the right jobs. Not everything can be Erlang, so you can't really rely on some of the Erlang distribution tool sets that you get through the language. And you might have other components. You might have services that live in the WAN. You might have different data centers that you need to communicate across. There's lots of different hosted providers out there. And you might even be communicating to specialty devices or embedded hardware. So the solution is AMQP. Anybody here heard of AMQP before? Very good. A lot of groups, a lot of the audience here. So why AMQP? Because it's a giant messaging toolbox. It gives you, it hides the physical network for you. It's extremely flexible. It gives you delivery assurances, and it's also a very high performance messaging bus. It's also backed by some very big names. So it's easy to come to companies who may be wary of your platform or wary of the messaging bus and say, well, this is a robust system. It's been around for a long time. It was vetted in the financial industry. So you don't need to worry about this particular component. And again, if you were using just native Erlang and stepping into an environment like that, then you'd have to get them into Erlang. You'd have to use direct message passing only unless you built up your own third-party wrapper or used other tool sets. And there is no built-in assurances, so you rely on the other side to tell you what happened. You don't really know if your message got there, if it was eaten by the WAN, or something was missed. And you have to represent everything as Erlang data terms, which sometimes is not necessarily the best thing, especially if you want to communicate to an outside world who may not want to suck down those terms. For instance, the JSON object or something like that, now you have to do conversions back and forth. So if you can keep them native, for instance, and just proxy them through, then that's a real win. So AMQP itself is an open binary wire protocol, so it's a very efficient protocol. And it was created by the JP Morgan group, or the working group was created by JP Morgan in 2006. It was actually started much earlier than that. And it aspires to be the sole business messaging tool for organizations. It's based around the concept of you have publishers that send messages into what they call exchanges. And let me just go ahead and put a real quick caveat on this. This is the current as deployed spec. The new spec is actually talking about possibly removing the exchanges as a redundant feature, but it hasn't taken a lot of hold yet. So we would have the exchanges that then put the messages into one or many queues, and those queues then push the messages, or the consumers fetch the messages, which would be the last component there. The middle piece in this square here is the actual AMQP component. So one of the really nice things about AMQP is there's lots of options. You're not locked into anything. So there's lots of brokers. I'm sure a lot of you have heard of some of these, like the RabbitMQ, which is the one that we primarily use. It's written in Erlang, which is fantastic. You can run it right alongside your Erlang stack. And there's lots of clients. Pretty much every language that we've ever come across, there's been a client, whether it was officially supported by the language, by one of the broker developers, or available as a third-party library. We've never had any problems with that. So when you're using AMQP, the basic principle is you publish a message to the broker, so you'll send him an AMQP message. It'll be received by the exchange based on the rule set they call the bindings. It'll go into various queues, and then the queues will then go to a consumer. You have several ways to actually send a message into a queue. You can do what's called a fan out, where any message that comes into the exchange will simply go to every queue that's bound to that exchange. And then each one is individually consumed by the consumer. I'm afraid this diagram makes it look like they kind of all come out. They go through one connection. But so your consumers all individually consume off their queues. You can also do what's called a direct exchange. So this is where, when the binding is created, there is a rule that is put into place. For instance, you might define it as key. And when it comes into the exchange, if the rule matches, so your routing key matches your rule, then that queue gets it. And that message can go to one or more queues. It doesn't have to be limited to just one. But it is an explicit match between the routing key and the rule. And then there's a topic exchange, which is the more flexible version of that, where when it comes in, you have, for instance, this pound, which means any of that segment. There's also a star component, which means any further after that. And you can see we can start to put things into buckets based on the actual message itself. So you might have, for example, USA News, which ends up in both the bucket News and USA. So when you're dealing with the WAN in AMQP, like I said, it's a fantastic tool set because they have a lot of the built-in tools for the assurance. One of the ways that they do it is message acknowledgement. And this is optional. You don't actually have to acknowledge messages. You can actually tell it when you get it out of the queue to automatically acknowledge messages. But this is a transfer of responsibility, saying that the message has been properly delivered to me. You can also take that a step further and say, I've actually properly processed the message, depending on how you architect your system. But this means that if you deliver a message to something over the WAN and it gets consumed, but they don't actually process on it, or it comes in corrupted, it can be redelivered because it wouldn't be acknowledged. This also gives you a lot of flexibility in doing things like knowing if your message has been delivered as well. You can use some of these systems. You can also get detection of undelivered messages. You can ask it to tell you if you put a message into an exchange that has nobody listening. It can tell you, well, there's no one there to consume this message. Or you can, with RabbitMQ particularly, they have built-in extensions that let you put timeouts on the message. And so that you know when that message hasn't been delivered within the time period and it becomes stale. RabbitMQ also has a fun exchange where any undelivered message goes to. So you can have loggers that live off of that and know when any message simply doesn't get delivered, and they can sort it out accordingly. And one of the really nice things is you have order preservation. So when you publish in a certain sequence, you get it back in that same sequence, and that's a guaranteed order, which is extremely useful when you're going across the WAN and things like that. Especially considering that AMQP can actually transfer very large payloads, including it can chunk a file. It's designed to actually transfer all of that data set. So it can actually maintain very large queues and keep the order of the messages as they come through that queue. It can also operate as a store and forward. So what you can do is you can throw the message in, and it doesn't necessarily have to be consumed. It can actually live there. And using some of the persistence flags that you have, you can actually keep that even through restarts of your brokers. So you can, for instance, have a transient worker that might be, say, a web browser that's pulling for events. And it comes up, asks for events. You see if there's any events for that particular session in a queue. That connection will then tear down, but events could still stack up in the queue for the next time that the page reloads or the long pull or whatever it is that you might be doing. So you can use this to kind of, to your advantage, to kind of leverage some of these modern technologies, or shoehorn them in to your existing platform so that they have an interface out to the outside world. And you can also use this for things like transient producers, where you might have one process that's constantly consuming, and all kinds of other producers over the various workers distributed out on your WAN come up, publish a message, and go away. And so that queue kind of is the way that they have left their impact. So one of the kind of thought experiments that I was proposing to somebody the other day, just as one of the kind of the cool flexibilities, is you could kind of share state this way. You could have a queue where the only thing you would ever do is put one message into that queue. You would then have another queue that represented all the work that you wanted to do. And all your workers would be attached to the work you wanted to do, in a special mode where only one message was delivered at a time. They would then fetch that state out of the queue. They would do their work. They would put the state back and acknowledge the initial fetch. And the acknowledge is effectively destroying the old state. So then the next worker would get the next job and be able to fetch the state. And as such, you can thread it through the workers. And the nice thing about this is using the AMQP protocol. If the worker that fetched the state crashes, he won't acknowledge it. All the jobs get redelivered because those consumers go down. If you put two states in, it still works because you can guarantee, since the order is guaranteed, you can do cleanup routines and things like that, and you know that the newest state will always be the last state. So it's kind of an interesting thought. I don't know that I would ever implement it, but it kind of shows you some of the power that this particular system has. So in implementation, you have to take into consideration the fact that it doesn't actually have a representation of the data you're sending. It can send binary data just as happily as it sends anything else. So you have to consider your target when you're actually implementing this. We chose to use JSON because that's the simplest and the easiest for the target audience that we were looking to publish messages for. So we normalized on JSON, but you might need XML so you can write, have schemas. You might need binary for its efficiency. You might even be talking to other Erlang libraries just so that you can use some of these like topic exchanges. So you might actually use more efficient Erlang binary terms. And you need to decide on your architecture as well. So there's two primary ways that you can take specifically the RabbitMQ broker, but you can cluster them where you have each broker can actually respond to any of the requests. And this is kind of more of an HA mode, where when you make your request to any one of them, they'll find the other one that actually has the queue on it and get the messages from it. And they have this kind of a shared state. But that has a performance penalty, or at least has in the past. They're still working on that one. And then there's you can federate. And when you federate, that's a one-way direction, and you lose some of the elements of AMQP because, for instance, you're making a copy of the message onto another broker. So you have to kind of be careful with that, but it's a good way to offload some of your work and things like that if you have like perhaps logging or something like that, and you just want to get it out of your primary broker, or maybe you have some alternate broker running on a different site for backup reasons or things like that. If you can live with that one-way direction, then that's a good way to go. We experimented with actually using federate to go in two directions, and I would recommend you don't do that. So where should you use it? So this doesn't replace the Erlang send. That's practically why we love Erlang. I mean, it's fantastic when you need to communicate between components, but even in our own stack, obviously we're still using the internal Erlang distribution mechanisms within the components themselves. Then the components talk to each other through AMQP, and that lets other things join in on that conversation as well. So this isn't the end-all, do-all messaging bus, but the power of it is when you use it to communicate amongst other elements, or use their assurances in the messaging to actually overcome some of the limitations of things like the WAN. So as an example, what I have here, oops, sorry, wrong one. This is the RabbitMQ interface. It's a little small. That's running on my local machine. And right now, this is just our application as an example up and running. But you can see that we've defined some exchanges. The top exchanges here that begin with AMQP dot are the AMQ dot are the default ones as defined by the protocol, and they'd be on every broker. The lower ones here This group here are the ones that we've actually defined for our applications purposes, and each one kind of represents one of the communications that we might be having. So for instance, we have things like call events coming through here, conference information coming through here. As you can see, we use quite a few topics, but we do have some direct exchanges up here, and some fan outs as well. We use the fan outs to find workers. So for example, when a request comes in for a call, we can fan out to any of the devices that might be able to respond to that call. They'll all send a directed response back, at which point we choose one and we notify them, and then we begin a one-to-one communication with that device, with that worker. So once you have the whole system up and running, you end up with something that looks a little like this, where you have on this side your queues. Let me find a good example. There you go. So you have your queues on the right-hand side, your exchanges on the left-hand side, and the messages based on the bindings will then flow into those various queues. And you can see that some of this, like the call.status.star, is going to be any call status event coming from the call events. But we also have bound specifically to switch.reload and channel.query. And then if we use our own queue name, that's where we're doing the directed. So that would be used for the one-to-one communication. One of the nice things as well is you don't have to name your queues. If you send up an empty queue name, these AMQP dot names are auto-generated for you. They're unique within a cluster, and so you don't have to worry about who's talking to what. You can just publish your message. So what does this look like when you actually put it into a product? So this is one example module that we have, obviously written in Erlang. But it's implementing something we call the gen listener, which is something that's it's a worker listening for events to come in. We define here a list of modules that will handle a certain class of events or a certain category of events. Our message structure itself actually defines these classes. And we can do bindings like, for instance, any directory request. And we define the bindings themselves. So the self here is a targeted message coming back to ourselves, and any notifications that are on the exchange for that notification. And what this will do is, if we look through the module, we simply start the gen listener is a wrapper around gen server. So we just start it with our options. We start it with this flag here that says basic QoS of 1. That's a mechanism that you use so that when you have multiple consumers consuming from the same queue, the messages will round robin from one to the other. So that means that you can start as many of these notifier processes as you want, and as you publish the message, you get one and only one message delivery to each one. Well, I'm sorry, not to each one, but each message will go to one and only one process. And that's the extent of this actual module. So all the work is actually being pushed off into these other modules, where in our particular case, they all come into this function called handle request, where we get a JSON object that was our actual original payload. What's actually going on here is less important, but the point is that once you actually have these bindings up, then the individual workers get the tasks that they need, they do their job, and they go back down. And this doesn't have to be in Erlang. Again, this could be a PHP component consuming the same notify events that these guys are and sharing in that workload, to put them on a web browser if you wanted to, or something along those lines. So the last component here that we've built out is, and this was the actual API definitions themselves. So these define what JSON elements the actual individual APIs will carry. And that is extremely important when you build these APIs, is to have a very clear and very rigid set of interfaces that you can go to and say, these are the things we expect, and everything else gets stripped off. Because when you actually are going out and wanting to integrate into other things, other libraries, then you run into all kinds of problems when you add in new fields, or if things come in an unexpected way. We had a customer, and I believe it was they were using Java, and the library, anytime you added a new header, if it wasn't explicitly defined, the whole library would just throw away the entire message. So You know, having an API set that lives in AMQP is great, but you need to be able to clearly define it. And that was one of the lessons that we learned. So we invented this sort of validator that strips everything off. So that's all that I have to say for that. If anybody has any questions, I'm more than happy to help you. Yes?
So how would you compare AMQP to 0MQ?
Okay. So the question is, how do I compare AMQP to 0MQ? I'm a little bit at a fault here, so I've never actually used 0MQ. But there's elements of it that I like, especially my understanding, of course, being that it's more peer-to-peer, more decentralized. I particularly like the AMQP way because for the way that we're distributing it, it gives us a lot more control. And we actually can come in and build up clusters in the data center and have kind of the hub and spoke architecture, which is more traditional, I guess, for me anyway. So, but again, I don't have a direct comparison for performance or anything else of that nature, I'm afraid. Any other questions or comments? Oh.
Oh, sorry.
No.
So, how many different implementation languages, either for producers or consumers, do you have using the system? Maybe you mentioned that, but I wanted to.
Not a problem. So our stack is entirely written in Erlang. We have people hanging off of the stack doing various things. So we have PHP and Java are the two primary that I know. I know that there's someone out there doing Python, and I believe that someone's doing something with Perl, but I'm not entirely sure on that one. So at the moment, not a whole lot. A lot more people are using our REST APIs. So this is a lower level a lower level entry into our system, obviously, but yeah.